Hey everyone, last time we learned about various matrix operations, the most important one being matrix multiplication. The others are important also, but matrix multiplication is especially important for this course. Now what we want to do, I'm going to discuss some properties of matrix operations. It feels like the lighting is a little funny here. I'm going to get in the way just for 1 second. See if I can get it a little brighter. Yeah, I think that's a little better. Okay, we want to talk about properties of matrix operations. So now I need some matrices, so let's let A, B, and C be matrices, and R and S scalars, so R and S are real numbers. Whenever these operations are defined, so when operations are defined, we have, and I'll show you what I mean by whenever they're defined. So this first property right here, A plus B. Well, A plus B is defined as long as both matrices are the same size, which means both A and B have to be M by N matrices. And it turns out, this is very easy to check, that A plus B is equal to B plus A. This is, and if you want to give this a name, this is the commutative property for addition. Part B, A plus B, in parentheses, plus C, so if you add A and B first and then add C to it, that's the same as doing B plus C first and then adding A to it. What would you call this property? This is the associative property for addition, right? So associativity means you can slide parentheses around. Property C goes like this. Multiplication is also associative. So AB times C is equal to A times BC. Now remember, the dimensions of these matrices now will have to work out so that the multiplications all work out. In the case that these multiplications are defined, it's okay to slide the parentheses around. Right, so that's associativity. Property D, A times B plus C is equal to AB plus AC. We call this the distributive property. And that's true on both sides. So here's the second distributive property. Here I'm multiplying on the left. It's also true when we multiply on the right. A plus B times C, it will be AC plus BC. There's distributive properties with respect to the scalars also. So R times A plus B is RA plus RB. So scalar multiplication is distributive. EFG. Here's another property involving scalars. Scalar addition is distributive also. So R plus S times A is RA plus SA. All of these properties are very easy to check. I'm not going to go through the proofs of these, but you can, if you like, go over them. A couple more properties. Property H, R times SA is equal to RS times A. It's kind of an associative property. I don't think this one actually has a special name. And this last one, R times AB, it's kind of an associative property also, is equal to RA times B, which is equal to A times R B. So what this is saying is you can slide constant multiplication or scalar multiplication wherever you like when you're doing matrix multiplication. All right, so here's some properties of matrix operations. We will use these whenever we need to, and in fact we'll use them quite a bit. Right? They'll be useful. I don't know that I'd recommend memorizing these properties. These are more things that should make common sense, and you should use them when needed. One thing to be aware of, matrix multiplication is not commutative. You cannot necessarily multiply matrices in opposite orders. It may not even be defined, and when it is defined, you may or may not get the same matrix. So let's write it like this. So warning, matrix multiplication is not commutative. So first of all, right, I mean, what that means is AB is not equal to BA in general. There's very rare cases where it works out, right? But most of the time it's not. I mean, for example, if you want to do AB, right, this would need to be an M by P, and this would need to be a P by N. Right? That's for it to be defined in the AB direction. And so now, if we have a P by N times an M by P, that would tell us, first of all, that we need M equal to N. So, for example, just to multiply in opposite orders, right, you could do a 2 by 4 times a 4 by 2, and then a 4 by 2 times a 2 by 2, right? The matrix multiplication will be defined, but the sizes of the resulting matrices are going to be different. So, in order for this to make any sense, for there to be any possibility that AB is equal to BA, you would want the sizes to be the same, which would mean that you would need your matrices to be square. Even then, so even for square matrices, AB is not equal to BA, except in rare cases. I mean, it does hold sometimes. So, but let's just look at an example here. So, here's my matrices. 1, 0, 1, 2 times 0, minus 1, 1, 1. All right, so I'm going to multiply these matrices, and so let's see. First, I'm going to get a 0, then I'm going to get a minus 1, then I'm going to get a 2, and then I'm going to get a minus 1 plus 2, positive 1. All right, so that's what we get if we multiply in this order. Now I'm going to reverse the order. 0, minus 1, 1, 1, 1, 0, 1, 2. And let's see what we get here. Minus 1, minus 2. This will be a 2, and then a 2. Right? So definitely different matrices. We get different results when we multiply these two matrices in different orders. So here's a definition. A matrix with all zeros is called a zero matrix. And the notation will typically just use a 0, capital 0 if you like, to stand for that zero matrix. So one thing to be aware of, so when we write this, this is some m by n matrix. When we do addition, this will need to be the m by n matrix with all zeros on it. And when you do this addition, you'll get an A. Also, if you do A times 0, where this zero matrix is any matrix that makes sense for multiplication here. So this would need to be an M by P, this would be a P by N, and what you'll get is the M by N zero matrix. Next definition, a square matrix with ones on the diagonal and zeros elsewhere is an identity matrix. We typically denote the identity or the identity matrix, so notation. Sometimes we won't care what the size of the matrix is. It's some n by n identity matrix, in which case we'll just write a capital I. If we need to be specific about the size, right, we want to specify the n by n identity matrix, I may write an I sub n there. That's in the case where I need to be specific. So for example, I2 is that matrix right there. Ones on the diagonal, zeros everywhere else. I3 is the 3 by 3 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Ones on the diagonal, zeros everywhere else. Now, one thing to be aware of, so I'm just going to say note. If we do any matrix A times I, where this matrix multiplication makes sense, what we get is the matrix A. And also if we do it in the reverse order, we'll say and I times A equals A. That's where the identity business gets its name, or that's why it's called the identity matrix. When you do the multiplication, A times I, out comes the original matrix A. And you can check this in general. Let me just give you one quick example of how this would work. Why is this true? So for example, let's try, we'll do this order right here. How about 1, 2, 3, 4 times the 2 by 2 identity matrix 1, 0, 0, 1. So notice what happens when we do the multiplication. So let's see, I'm going to take this row dotted with this column. That will give me a 1. Then it will give me a 2. Then we'll get a 3. Then we'll get a 4. And you can check if we reverse the order, same thing would happen. So, and you can check this in general, no matter what the sizes of the matrices are. When you multiply on the left or the right, whenever it's defined, matrix multiplication satisfies this property right here. Okay, so our next definition, so let's let A be a square matrix, let's say n by n, if there exists an n by n matrix, call it capital B, such that AB equals the n by n identity matrix, which equals B times A. Then matrix A, So then A is invertible or non-singular. So invertibility or invertible and non-singular are used interchangeably. Most of the time I use invertible. Otherwise, A is singular. So a matrix, an n by n matrix, is either invertible or singular. It can't be both. One or the other has to happen. B is called an inverse of A. So B is an inverse of A. So for example, let's say A is this matrix right here, 2, 3, 1, 1, and B is the matrix -1, 3, 1, and -2. So let's just check. If I do A times B, that will be 2, 3, 1, 1 times -1, 3, 1, -2. And let's see what we get. First, so I'm doing top row dotted with first column, and that will give me a +1. Then I'm going to get 6 minus 6, that's 0. Then I'm going to get -1 plus 1, that's a 0. Then I'm going to get a 3 minus 2, that's a 1. And if you do the multiplication in the opposite order, you're going to get exactly the same thing. So I'm running out of space here. 2, 3, 1, 1. So that's BA. So in this case, what we would say is the matrix A is invertible, and B is an inverse for A. Now, so suppose let's start with an invertible matrix. So suppose A is invertible, and B and C are inverses. So what does that mean then? Well, so that means that AB is equal to the identity matrix, which is equal to B times A. I don't need to put an I sub n here. It's whatever the dimension is. That's what it is. And it also means that A times C is equal to the identity, which equals C times A. All right, so now what does that mean? Well, so that tells us we can say well, I've got AB equal to the identity, I've got AC equal to the identity. Putting those together, what we have is A times B equals A times C. Okay. So now what I'd like to do, I'm going to multiply on on the right hand, on the left hand side, I'm going to multiply both sides by B. And now we need to remember back one of our properties. So I multiplied on both sides here by B. One of our properties is that matrix multiplication is associative. So that would mean that BA times B equals BA times C. Now, what do we know about BA? Well, BA is the identity. So now we have I times B equals I times C. But wait, I times B is B. I times C is C. So what this shows us is that B is equal to C. So what did we just do? We just proved a theorem here. So let's call this theorem. What we showed, if A is invertible and we have a couple of matrices that behave like inverses, they actually turn out to be the same matrix. So inverses are unique. So let's label this uniqueness of inverses. How do I want to say this? If B and C are inverses of A, then B is equal to C. So notice when I defined inverse, I said B is an inverse of A, leaving open the possibility that there could be multiple inverses. Now what we see is that can't happen. So I can now say the inverse. So in light of this theorem, we can say the inverse of A, and now we have special notation to indicate the inverse. We write B equal to A inverse, and so the inverse is now written. The notation that we use, A raised to the minus 1, denotes the inverse of the matrix A. All right, we have this idea of inverse matrix, right? And there's if you have an invertible matrix, that means that there is some matrix which we will now write as A raised to the minus 1, such that A times A inverse equals the identity, which equals A inverse times A. Now, the next thing we're going to need to do is figure out how to identify when do we have an invertible matrix, and if so, who is the inverse of that matrix? So we will develop a general procedure for producing inverses. And in fact, this procedure will allow us to decide if you're handed an n by n matrix, it will either produce the inverse or you will stop and say, this matrix does not have an inverse. It's a singular or non-invertible matrix. So we will develop a general procedure for doing this. For now, we concentrate on 2 by 2. So we're going to develop a procedure. We'll identify who the inverse of a 2 by 2 matrix is. So let's take a general 2 by 2. If A equals the matrix A, B, C, D, I'm going to write this as little delta. Let delta equal AD minus BC. It's possible that you recognize this right here. This is the determinant of the 2 by 2 matrix, so AD minus B times C. Right? You might have learned this in 143. Okay. Now, in the case, so this could be 0, it could be non-zero. In the case that delta is not equal to 0, let, I guess I'll call it B for now. So let's let capital B be the matrix 1 over delta times, that's right, so D goes here, A goes here, and then I want to negate the B and the C. So what did I do? I interchanged the roles of A and B, A and D, and then I negated B and C, but left them in the same spots. So then, if we do A times B, that's going to be A, B, C, D times 1 over delta D minus B minus C, A. notice why I needed to work in the case that delta is not equal to 0, because I need to write this fraction 1 over delta. One of our properties of matrix multiplication tells us that I can slide this constant out front and do the multiplication A, B, C, D, D minus B minus C, A. That's 1 over delta. Times, all right, what do we got here? This will be AD minus BC. That's delta. Then I'm going to get negative AB plus AB. That's a 0. Then I'm going to get CD minus CD. That's a 0. And then the last one, hopefully you can see this, the last one is negative BC plus AD. That's delta. And so, what do we get when you multiply this through? 1 over delta times the matrix delta 0, 0 delta. That is the 2 by 2 identity matrix. You can see this. Oh yeah, it looks like it's showing up. You can check if you multiply in the opposite order, you'll also get the identity matrix. So BA is also equal to the identity matrix. So what we just did is we produced the inverse for the 2 by 2 matrix A. So let me write this down. So conclusion. I don't know that I need to write this as a theorem, so let's say it like this. So if A equals A, B, C, D, and delta equals AD minus BC is not equal to 0, then A inverse is equal to 1 over delta times D negative B negative C A. Okay, so there's a nice formula, and so here's the deal. This is the formula for the inverse, which means that in the case that the determinant, this delta value, is not equal to 0, the matrix is invertible. In the case that it's 0, the matrix is not invertible. It's singular. Inverses, this is an important aspect of linear algebra. And here's the first use. So we'll say application. Solving linear systems. Last time, one of the things we saw is that a linear system can be expressed in terms of a matrix equation. So consider the linear system, which I'm going to write now in matrix equation form. AX equals B. So remember, this is the coefficient matrix right here. X is the vector that holds all the variables, and then this B is the column vector that tells us the constants on the right hand side of each equal sign. So consider this linear system where A is invertible. So suppose you're handed a linear system, you rewrite it as a matrix equation like this, where it turns out that this coefficient matrix is invertible. Then, if I multiply both sides of this equation by A inverse, on the left-hand side, I'll have A inverse times A, which goes away. So then we will have X on the left-hand side. On the right-hand side, we'll have A inverse equals B. And that will tell us exactly who the solution set to our linear system is. So let's look at an example here. So as an example, I want to solve the system, 2x plus 3y equals 1. 2x plus 3y equals 1. And where'd it go? Oh, x plus y equals 2. Okay, now I can rewrite this as a matrix equation. In the form ax equals b, it's going to look like this. My coefficient matrix will be 2, 3, 1, 1. My column vector bold-faced x will consist of the variables x and y. And then on the right-hand side, my vector, column vector b, is the column vector 1, 2. Delta, let's see who that's going to be. That's going to be 2 minus 3, so that's negative 1. So if this coefficient matrix, if I call that coefficient matrix capital A, then A inverse is going to be 1 over minus 1 times. All right, so what do? We reverse the roles of these two right here. So this will be a 1 and a 2. And then I negate the off diagonal entries. Minus 3 and minus 1 go there. This will be the matrix negative 1, positive 3, positive 1, and negative 2. So what? Well, I'm about to erase it, but what it tells us is that x is equal to A inverse times B. So let's do that now. So x is equal to A inverse minus 1, 3, 1 minus 2 times B, which is 1, 2. And if we multiply this out, let's see, I'm going to get negative 1 plus 6 is 5, and then I'm going to get 1 minus 4, so that's a negative 3. So what does that tell us? That our solution to the original system is x equals 5, y equals negative 3. Check it. Plug 5 in for x in the first equation. What do we have? 10 plus negative 9 equals 1. Yep, that works. And 5 minus 3 equals 2. So, in the case that the linear system corresponds to a coefficient matrix that's invertible, then finding the solution amounts to, or one way to go about it, is to find the inverse matrix, multiply both sides by the inverse matrix. A little bit of notation. We'll sometimes need to take a square matrix and multiply it by itself, sometimes multiple times. So if A is square, then we can define A to the K, and what that means is A times A times A, right, K times. Also, we can define A to the minus K in the case that it's invertible. Right? This is A to the minus 1 times A to the minus 1. So if you have K factors of the inverse. It was sunny and now it's starting to rain out there. We're going to end with a couple of facts here. So first, I'd like to collect some properties of inverses. All of these are fairly, I'd say, self-explanatory or obvious. So let's see. Let's let A and B be invertible. n by n matrices, and I need some constants, let's say k, greater than or equal to 0. The first fact, it turns out that if you multiply two invertible matrices, you get an invertible matrix. And the formula is easy to see. The inverse of A times B is B inverse times A inverse. Check this. Explain to yourself, show to yourself why this is true by understanding what it means to be an inverse of A times B. Property B. The inverse of the inverse is the original matrix, so A inverse inverse is A. Part C, A to the K inverse is A to the minus K. And the last property here, R times A inverse, so the inverse of the matrix R times A is 1 over R times A inverse. All of these are easy to check. I suggest that you do. You can also, I think, find this in the book. One more, so then we're going to end with this. So properties of transposes. Okay. We're going to come back and transposes will show up later on in this class, so let's get this, put this together. So I think this is pretty obvious. Remember, transpose means flip the matrix or flip the roles of row and column. So if you take the transpose of the transpose, guess what you get? You get the original matrix back. Part B, A plus B transpose is A transpose plus B transpose. So that's a nice property. Transpose also works nicely with scalar multiplication. The transpose of, that should be an A right there. So the transpose of the matrix R times A is R times A transpose. This next one, I think this is less obvious, but the transpose of A times B is B transpose times A transpose. And then one more property, let's put it right down here. The inverse of the transpose is the transpose of the inverse. So transpose works, this operation of transpose works nicely with all the operations, right? Addition, scalar multiplication, multiplication, and inverses. Okay, so that's a good place to stop for today, and I'll see you next time.